Good morning. My name is Eric Butterfield. I'm the document prep for Design Team 8. That's Team GUIMOO. Our team, sponsored by the National Science Foundation and Dr. Chakrabarti, were facilitated by Dr. Renjian. And with me are my group members Samuel Richter, he's our presentation prep. Manglen Lee is our lab coordinator. Dan Perez is our webmaster. And finally, Tabula Mbalakanga is our team manager. Today we will be giving a technical presentation on RFID and the UMass Moo WISP that's being developed to implement RFID. So, an agenda for what we're going to go over today. I'm going to start by giving a high-level background introduction into what RFID and the UMass Moo WISP are. Sam's then going to further explain how RFID works, and Dan's going to talk about how the backscatter communication between tags and RFID readers work. Tabula will then talk on DC to power harvesting and DC to DC up conversion, which is how these devices power themselves. And finally, Manglen Lee will explain the variances in the UMass Moo hardware as compared to regular RFID tags. So what exactly is RFID? RFID stands for radio frequency identification, and it's a wireless non-contact system that uses radio waves to transfer data. It's very popular in everyday Americans' lives. If you've ever been to a store, the anti-theft devices are all done via RFID. If you ever bought a product and opened it up and found what looks like a sticker with a spiral design on it, that's probably an RFID tag, and it's read by the scanners you walk through when you leave the store to make sure you're not stealing anything. Other popular uses include animal tracking, e-passports, which one day are hoped to phase out the old paper and stamp method, and inventory systems. RFID as a technology is growing exponentially. Currently it's a $7.5 billion industry, but in just 2 more years, so by 2014, it's predicted that it will be a $20 billion industry. So now that we know a little bit about what RFID is, what's the Moo WISP all about? Well, the Moo WISP is an alternative to standard RFID tags, and it can do a lot more than them. WISP stands for Wireless Identification and Sensing Platform. It behaves as if it's a passive, meaning batteryless, computational RFID device. This particular WISP is capable of integrating together RF energy harvesting, DC to DC conversion, an MSP onboard microcontroller, double EEPROM non-volatile memory, digital I/O, capacitive and voltage sensing, and a slew of sensors including an accelerometer. As for why it's called a Moo, by the way, since it can do all of this, it's known as the beefiest device in its category, so someone put that together as being a Moo. So how is a device that's able to do all this work when it doesn't even have its own power source? As you can see, there's 3 main parts that work together on this device. There's the antenna front end, the digital hardware, and the sensors that include the accelerometer and thermometers. A regular RF tag will stop after this point. This Moo gives us the ability to have the microcontroller and sensors as well. To better understand how this works with the RFID, we first need to look a little bit more at RFID with Sam.
Thank you, Eric. I'm Sam, and I'll be covering some of the general functions of RFID. As Eric stated, RFID stands for Radio Frequency Identification. This is a reader that communicates with a pair of tags that have identification codes on them. Unlike traditional computer-based identification systems such as barcodes, this system does not require a line of sight. Each tag has a 96-bit electronic product code. This is read by the reader and contains a header that tells the reader what protocol the tag is using, some data, an object class, and an individual serial number for each tag. These tags can either be passive or active. The passive tags, like the Moo WISP that we use, they only send information and turn on when prompted by the reader, whereas active tags usually have their own power source and continuously transmit data to the reader. Now these tags over the years have been miniaturized. Hitachi currently has the smallest one at 50 by 50 micrometers. But the size of these tags is only limited by the antenna, which is used to harvest power and send out messages to the reader. In this picture right here, you can see the University of Bristol actually used some of these miniature tags to tag ants to be able to analyze the behavior of the colony. So, the way RFID communicates, it uses EPC Gen 2 protocol. This protocol sets standards so that all readers can communicate with all tags. It's designed for passive tags, where the reader will talk first, initiate the tag, and then listen to the response message from the tags. With this protocol, the reader can either read information from the tags, it can write data to the tag's memory, or it can kill the tags, such as when you're at the store purchasing an item and they scan it at their little scanner at the desk. That kills the tag so that it no longer responds to any readers, specifically when you're walking out the door to that security system. This protocol avoids data collisions using the slotted Aloha protocol, and it ensures spectral control using frequency hopping spread spectrum. I'll be going over these two techniques next. It uses slotted Aloha to send its data. This is where a single reader can communicate with multiple tags over a shared transmission medium. This is a random access data transmission with slotted packet durations. As you can see here, you have a few tags and you have time slots at which they send messages. So when the reader sends a message to the tags, every tag responds at a random time interval after they receive the message during one of these slots. So as you can see, sometimes more than one tag will send a message in a certain slot. This results in a data collision. The reader will then be able to detect this collision and disregard that data. Any other time slot that only gets one message from one tag results in a successful transmission of data. When the reader sends a message out to the tags, it uses frequency hopping spread spectrum technique. This is where the reader sends a message over multiple bands of frequencies. And as you can see here, it compares the messages that are responded by from the tag, and if they correlate, that results in a successful read. As you can see here, since you're sending it over multiple frequencies, the same message, it kind of creates a signal that looks like white noise. This white noise provides security since no outside signal at a certain frequency is going to be able to interrupt every message sent at all the frequencies, and also since it is white noise and it looks like white noise and it's over a broad band, it's hard for people to intercept the signal because it's not on one single band. I'm going to pass it on to Dan, who will talk a little bit more about how these signals are sent.
Hi, I'm Dan Perez. I'm going to talk to you a little bit about some of the basics of RFID tags and backscatter communication. The communication process begins when the RFID reader sends a radio signal to the RFID tag. This signal has two purposes. First, to send data to the RFID tag, and second, to provide power to the RFID tag. So the RFID reader uses two methods to accomplish this, amplitude shift keying and pulse interval encoding. So this diagram illustrates both of those principles in use. You can see that a carrier wave is being, the amplitude of a carrier wave is being modulated. For reference, the Class 1 Generation 2 protocol uses a carrier wave that operates between 860 and 960 megahertz. So for amplitude shift keying, what's important to note is that the amplitude isn't pushed all the way down to zero. There's always some amplitude left to ensure that power is always being delivered to the RFID tag. Pulse interval encoding simply means that zeros and ones are encoded with pulse length. So a zero is represented by a short pulse length, a one's represented by a long pulse length. The RFID tag communicates back to the RFID reader by using backscattering. So this is a principle that many of you are probably familiar with. When the radio signal from the RFID reader reaches the antenna of the tag, The electromagnetic wave drives an electric current on the antenna. As the electric current on the antenna varies, it produces an electromagnetic wave that gets reflected back to the reader. So the RFID tag is able to encode data onto the reflected signal by modulating the amplitude of the reflected signal. It accomplishes this by varying the impedance between the antenna and ground. So when the impedance is low, the amplitude of the reflected signal is high. When the impedance is high, the amplitude of the reflected signal is low. So RFID tags rely on a protocol that only counts state changes to encode data. So the RFID reader doesn't need to know the exact state of the signal that left the RFID tag. The RFID reader only needs to count state changes of the signals that are coming back to it. So this method is known as frequency shift modulation. I should note that what's being modulated is not the frequency of the carrier wave. The frequency of the reflected carrier wave is exactly the same as the frequency that came into the RFID tag. What's being varied is the rate at which the RFID tag is modifying the amplitude of the reflected signal. And there are several protocols that Gen 2 uses that use this principle. FM0, Miller 2, Miller 4, and Miller 8. So to see what these protocols actually do, how they actually encode data, it's probably best to take a look at a specific example. Since the MOVE-WISP uses Miller 4 encoding, that's the example we'll look at. So 4 just means that each bit of data requires 4 cycles to be transmitted. So a 0 is distinguished by 4 state changes every 4 cycles, and a 1 is characterized by 3 state changes every 4 cycles. Something else to note here is that when transitioning between 0 and 0, the state of the amplitude remains the same. When transitioning into or out of a 1, the state of the amplitude switches. So hopefully that gives you a basic idea of how backscattering works and how data is encoded onto a backscattered signal. Next, Tabula is going to talk about power harvesting.
All right, thank you, Dan. As Dan mentioned earlier, my name is Tabula, and I'm going to be discussing power harvesting. So, in discussing power harvesting, you must be wondering, where does it fit in all together with an RFID? Well, as Eric mentioned earlier, RFIDs are passive, meaning that they don't have batteries in them. And so in order to be able to power the RFIDs, what happens is we use power harvesting by taking, to derive energy by converting ambient sources into electrical energy, capturing it and storing it into the devices for further use during the required purposes. There are many methods of harvesting energy, many sources, from ambient radio frequencies, which are the ones that most RFIDs use, where we take the radio frequency and we convert it into electrical energy to power the device. There are thermal, photovoltaic, we have pyro, as well as piezo, which was mentioned earlier on. These methods are used for different RFIDs as well as different systems. And in the use of these devices, most times the power that's being used isn't enough to empower the entire device. For example, if we have an RFID, as the RFID gets further and further away from the antenna, you'll see that the power produced by the power harvester becomes less and less efficient, which means that there has to be a way to amplify that power to be able to generate enough for the entire circuit. To do so, what we use are DC to DC converters, up converters. Now, what is a DC to DC converter? DC to DC converters are integrated circuits that are used to either step up, step down, or invert the voltage and current being applied to a specific circuit, such that, for example, a linear rectifier rectification will take in an input and it will output a voltage that is less at a lower level than that of the input. When it comes to switching, what happens with switching is that an input voltage enters the integrated circuit, and that voltage or power is stored inside an energy storage device, and then is then used later on to amplify or reduce the voltage, the output voltage, in comparison to the input voltage. And so there are several methods of doing so. We have magnetic, which usually uses transformers or inductors, and we also have capacitive, which usually uses capacitances as the energy storage devices. And so In regards to RFID, most times capacitive switching is what is used. And an example for that is this is pretty much a high-level drawing of an RFID. And we want to zoom in more towards the power harvester, which this is a 5-level step-up converter. And most of us have seen this in ECE 302. But basically what happens is that this circuit board is composed of capacitors and Schottky diodes. The diodes behave as switches, and as the switches open and close, it allows for the capacitors to charge and then to discharge onto the entire IC, such that the final voltage going out can be boosted and multiplied 5 times the original rate. I will now be passing it down to Mong Lin, who's going to be discussing further impedance matching as well as voltage rectification, and compare the difference between a regular RFID sensor and the MOO sensor.
Okay, thanks for the tableau. And now, from here is all the components that the general RFID will have all together. So for the RFID harvest part, it will harvest energy from the RFID readers. So it's kind of battery free, which avoid for the filter change of the battery. Also, it will have a capacitor near it to store the additional energy for the later use. And also for the impedance matching part, it will match the impedance between the antennas and the rest of the circuits. The way for doing it is like connect the hardware to the computer and use the signal analyze software to find the signal that's reflected and absorbed by the antennas to find the best impedance for the most efficiency signal transmission. And for the voltage regulator, it will adjust the voltage that supplied to the rest of the circuits to improve the efficiency of the RFID. So for the demodulator and the modulator part, for demodulator, it will have the comparator on its receive side to receive the voltage from the antennas and to keep a kind of balance between the antennas and RFID readers. And for the modulator, is that to help the better communication between the RFID readers and antennas. So from here, you can see this is an antenna front end. This is the general RFID we'll have all together. But for the MOO hardware, it also have some additional part like MSP413, which is microprocessor, and the sensor part. So this is a structure of the microprocessor of the MOO. It have 16 pins inside of it, which is connect functional components that I have discussed before. And also it will have some free pins for users to connect other devices for the additional use. And the working limit is like 1.8 volts to 3.6 volts. And the RAM is like 8K. And also it supports that external flash, which the working limit is like 1.6 volts to 1.9 volts. And for the DC to DC converter, it should connect the microprocessor and external flash, which means they should work at the same voltage for the well function. So for the sensor parts, the MOO has supports all different kinds of the sensors, like the temperature sensors and accelerometers, LED sensors, and the voltage sensors. So for the temperature sensors, it will detect the temperature where we put where the RFID have put in. And for the accelerometer, it will determine the 3D rotation of the objective objects with respect to the RFID. And for the voltage sensors, it will measure the voltage supplying to the rest of the circuits to have the users to check whether the circuit works right or wrong. And for LED sensors, it will show which sensors were current working and which are asleep. And also it supports for the external sensors for users to have some additional uses. So I will pass to Eric who will describe conclusion of
So, just a recap of what we've gone over today and what we've learned. We introduced you to RFID and the UMass MOO, and then we explained further how the UMass MOO and standard tags can communicate with RFID readers. We then talked about how these devices can power themselves without any sort of power source of their own, and the differences between the MOO device and standard RF tags. At this point, if there are any questions, please feel free to ask. If not, thank you, we've been great.
I have a question.
Yeah. For who?
Can you hear me?
Yeah.
Yeah, how do they disable an RF tag? I
Uh,
think it was Sam who mentioned it.
Right. The killing the tags.
Each tag just has its own circuitry to it, so it's just kind of a coding thing. It just sends a message that prompts the tag to not respond whenever it receives further messages. So it just disables the tag from ever sending out information again.
So is it a permanent, like it burns something, it burns a connection?
Yeah.
Or it,
It's
resets
more
something
for
on the tag?
product uses.
Because it has to be active if it's gonna reset something on the tag, I'm a little confused.
Right, the tag is active, such as like in the store, when it's on the product. So it's active so that if you take it out, the reader will be able to pick up the tag, and when it picks up the tag, it turns on the alarm. When you go to the counter, they put it over the scanner, it sends a message, a kill message to the tag. There's a specific register in the tag that will then be turned on, and
Does it
that
really-
will,
Does it really kill the tag? or
Yeah,
maybe
because
just,
when you're at the store and you have a
validate
product,
the
you
tag's
don't-
ID?
yeah, when you're at the store and you have a product with an RFID tag and you take that home, there's no reason for you to have an RFID tag that is still functional when you take it home, because it's only for use at the store and has no further uses once you purchase it and leave the store. So that tag no longer needs to be used ever again.
Well, yeah, I understand that, but it doesn't really kill it then, it just invalidates its number, so if it's detected, it just says, it's already been checked out, for instance. I don't think it can kill it.
I believe it does.
It does, alright.
Yeah, that way it does not, yeah, that way it doesn't hog up any of the bandwidth and just distract the reader. It's just, it's dead, it doesn't send any messages, the reader doesn't have to worry about it. But there are also other, there's, oh, sorry.
Good job.